Hello everyone, welcome to another video. In this video, we'll go over a relatively easy topic, capacitors, or things that look like this. You might have encountered them a lot, or you might have seen some circuits, and most of them at least use one capacitor. Now, what are these? They're kind of similar to batteries, but not really batteries. In its simplest form, they're just two conducting metal plates separated by a insulating material called a dielectric. Now, you can have airspace in between them, like not any material but air, but it isn't very efficient. Now, from this diagram, you can see there are two of them. One is just two plates separated by nothing but air, but that really takes up a lot of space and really isn't efficient when you're trying to go small. But with a dielectric, you can really roll it up and give this its iconic cylindrical shape. So anyway, I mentioned that these are like batteries, and like batteries, they store energy. But not with chemicals though. They store separated charges. So let me explain. So if I connect a battery to this capacitor and attach voltmeters and ammeters and all of these measurement stuff, and I've labeled the terminals as well. So what happens is this: electrons, they move out, they get repelled from the negative terminal, and they flow through the wire and settle on this plate. So an electron gets settled, and that, because of its negative charge, it's going to repel an electron from this metal plate, and that electron is also going to get attracted by the positive terminal. So that electron is going to flow through the wire and into the positive terminal. Okay, so one goes into one plate and another electron comes out of the other. Okay, and because there is a flow of electron, this ammeter measures a current, and that current is maximum at the start because it didn't really experience any kind of repulsion as of now. So initially the current is maximum. But what happens if you just let the circuit continue for a while? Well, after some time, it will have enough charge, it will have enough negative electrons on this plate and enough positive electrons on this plate that the electron is going to experience the same amount of repulsion from this plate and the negative terminal. So it's going to experience the same repulsive force, and so it's not going to move. And here, if an electron just tries to go out, it's going to experience an attraction towards this plate, and it's going to experience an attraction towards the positive terminal. In both cases, if the attraction both the attraction are equal and both the repulsion are equal, the electron doesn't move. And because of that, the current when the capacitor is fully charged is going to be 0 amps. But really, what does it mean that the capacitor is fully charged? Now, a capacitor being fully charged means that its voltage, the voltage across these two plates, is equal to the voltage difference, or potential difference, between these two terminals. Now, why does that happen? Really, why do we need the capacitor to have the same volts as the terminals of a battery? Well, charges move from high potential to a low potential region. Just like if you place an object on a smooth incline, it's going to move downwards. So what happens when the capacitor is fully charged is that this low level is increasing in its height until it becomes really level. I guess that's a pun. Anyway, level with the potential of the battery. And because of that, electrons don't move. Electrons will never move from a region with no potential difference. You need to allow them to moves from a high potential to a low potential, just like a slope. Okay, so some people, they really ask a lot of questions. Well, it's normal. So how much charge is stored on the capacitor? We've seen that electrons get stored on on one plate and electrons move out of the other plates. So how much charge does a capacitor store? Well, I mentioned for every electron that gets deposited on this plate right here, an electron moves out of the positive plate. So if the negative plate stores negative 5 coulomb, the positive plate must store positive 5 coulomb, and they really cancel out. So you have a net charge of 0 on the capacitor. But let's ask a more interesting question, that is how much charge, or what's the amount of charge that's stored on one plate of the capacitor? Well, for one plate of the capacitor, you have a formula, which is, I got Q equals CV. The C right here is the capacitance of the capacitor. So in a sense, the number of charge, or the amount of charge that's stored, it depends on what capacitor you're using and what's the voltage between these two plates, or what's the voltage of the power supply. So the charge is stored on one plate is given by Q equals CV. C is the capacitance, and what C is how many, C is written as Q by V. What C is how many charges are going to get stored, or what's the amount of charge that can be stored on one plate of the capacitor if 1 volt is applied between them. So if the potential difference between them is 1 volt and it stores 50 coulomb of charge, then the capacitance is going to be 50 farad. Now farad is a huge quantity. What farad is, let's actually define the unit. A capacitor has 1 farad capacitance if it stores 1 coulomb's charge when 1 volt potential difference is applied between the plates. Applied between plates. Okay, so far so good. So 1 farad, as I mentioned, it's a huge amount. So mostly, if you're going to deal with capacitors, you're going to mostly see microfarads or nanofarads or picofarads. So anyway, capacitors, they have multiple use cases. Now, the first one I mentioned, it's used for storing energy, but there are other uses as well. It could be used in time delay circuits. It could be used for smoothing out AC current or rectified current, but we're going to discuss those in a later video. So how does blocking DC work? Well, I mentioned that when the capacitor is fully charged, there is no current. The current is going to be 0, and that is how it blocks DC. So the direct current can't flow anymore. But that it can't block AC at all. Because for AC, the terminals, they switch positions. For the terminals of the AC power supply, it's going to really switch position. At one instant, it's going to be negative. The left one is going to be negative and the right one is going to be positive. At the other time, the right one is going to be negative and the left one is going to be positive. And because of this oscillation, any charge that gets stored here moves out again and then comes back in and keeps on oscillating. And because of that, it never really resists or stops AC current. And also, I told you that they have an insulating material between them, so the resistance is huge. They have huge resistance, almost infinite. And that's an idea that's going to help you when you're doing calculations, specifically with A-level physics. Now, storing energy. It's a buzzword for capacitors, and that's going to be the crux for today's video. So you see that capacitors, they have the charges separated. You have charges divided between a positive plate and a negative plate. You have charges divided between a positive plate and a negative plate. So separated charges. And because these charges are separated, they're going to have electric potential between them. Okay. Because these are opposite charges and they like to stay as close as possible to one another, and to separate them you need to do work on them. You need to give them potential energy, and that's electric potential energy. So you did work to separate charges, and when it comes to capacitors, let's actually try and find out how much energy is stored in the capacitor. But before we figure that out, we need to understand what volts mean. So by the definition of volts, it's energy. Volts is energy per unit charge. So how much energy is given to 1 coulomb charge by the power supply? By the power supply. So in this, we have a 1 coulomb charge getting 10 joule. So the power supply that gave it energy, or the motivator, I would say, has 10 volt as potential difference. And I guess this was a very lame joke and everything. I wouldn't really call it a joke. And all of you would be giving this reaction. It's pretty normal when I get it often, I guess. And by the way, this guy is Alessandro Volta. He's the namesake for the unit volts. So anyway, volt is the energy per unit charge, or how much energy is carried by each unit charge. So this guy has 10 joule of energy and as a charge of 1 coulomb. So we could rewrite it as energy. We could rewrite it as energy equals voltage multiplied by charge. Okay. So if I have a graph here of voltage and current, so let's draw a graph. On the y-axis, we are going to have the charge, and on the x-axis, we are going to have voltage. So by looking at this, we can, thinking in terms of areas once again, area under a QV graph is going to give us the energy stored by the capacitor. So how should the graph look like? So well, recall the formula, Q equals CV. So the charge stored on one plate is directly proportional to the voltage between the potential difference between the plates. So if it's directly proportional, it's going to be a straight line passing through the origin. And let's find the area under this graph. So the area under the graph is going to be, it's going to be half QV. That's going to be the energy. Okay, but we can have really different variations from it as well. Well, we are going to use this. Q equals CV, so instead of Q I can write CV. So that's going to be CV into V. So we have 1/2 CV squared. So this is one of the common formula that you're going to use if you're giving A levels, but you could really use another one as well. So instead of V, we could write it as V equals Q by C. So we can also write it as 1/2. Instead of V, we're going to write it Q by C. So that's going to be Q squared by C. So this is another formula that you could use. But it's really advisable to just learn one and learn how to derive the other ones from it. It's just much easier and really gives you a proper understanding of how all of these formulae come into being. Now, every capacitor has a safe voltage limit. Let's consider this right here. Let's say it has a safe volt of 10. So what happens if I try to increase? That doesn't happen. So, realistically speaking, something like this happens. While you're done with these explosives, check out ElectroBOOM for more explosives. I mean, more education on electric circuits, but after finishing this video. So let's say you have a bunch of capacitors lying around like a normal person, and you want to create something fun out of it. And like a very normal person, you don't have capacitors that you need, except that you have like 2,000 of them lying around. So you can really combine capacitors in different ways and see how they work. So let's say you don't really have a 30 farad capacitor. You don't really get these very often. So let's say you need a 30 farad capacitor, but you don't have one. So how do you get one? Well, you can buy one. Well, cringe aside, if you can buy one, you can use physics. So let's say you have a 10 farad capacitor and a 20 farad capacitor instead of having that 30 farad one. So how can you use these to make a 30 farad capacitor that you need? So you can connect them in parallel to get the 30 farad capacitor. But how does that work? Okay, see. So let's have, sorry, this messes up quite frequently. Anyway, so let's say you have a 10 farad capacitor, and in parallel you have a 20 farad one. So you have a 20 farad capacitor, and then you have a 10 farad right here, and these are connected by a circuit. Sorry for these really hideous diagrams. Not very good at it though. So you have the battery right here. So let's say you have a 10 volt power supply, just to be safe. So in a parallel circuit, the voltage remains same. The voltage across these parallel units remain the same. But why? Because voltage, as I said, is energy that each charge carries. So let's say that you have that the power supply gives out 300 coulomb of charge, and it travels across the circuit through the wires, and it gets divided. So every coulomb of charge that travels through this path is going to have a 10 joule energy, because the battery has 10 potential difference of 10 volts. So every coulomb is going to have 10 joules right here. So that means all of the charges have 10 volts, but a potential difference of 10 volts. And every charge that moves through this path is also going to have 10 joule of energy. And 10 joule of energy per unit charge means this circuit, the potential difference across this is also going to be 10 volts. Okay. But the charge itself, all 300 coulombs of them, divides. So to maintain the 10 volts, this 10 farad capacitor, remember the formula, Q equals CV, so V equals Q by C. Anyway, so to maintain the 10 volt potential difference, the 10 farad capacitor needs to store, the 10 farad capacitor needs to store 100 coulomb. And the 20 farad one needs to store 200 coulombs. So 200 coulomb of charges move through this path, and 100 coulomb of charge moves through this path. Okay, that makes sense. So based on what we know, let's set up some equations. So current in the entire circuit is going to be current across path 1 plus the number of charges that move across move by using path number 2. Okay, so far so good. So let's attach it with let's substitute them with other values. So we know Q is CV. So instead of Q, we can really write CV. So C total, which is the capacitance of the entire circuit, multiplied by potential difference across the battery, is going to be equal to the capacitance of one of the capacitors in parallel multiplied by the voltage across it, plus capacitance of the second capacitor multiplied by the voltage across it. Now we have clearly established that the voltage across all of them there is going to be equal to the voltage of the power supply, because voltage in parallel or potential difference in parallel systems, they're going to be the same. So we can really factor them out. So we get this. Capacitance of the total circuit is going to be equal to the capacitance of the individual capacitors if they're connected in parallel, as we did here. If they're connected in parallel, as we did right here. So we had a 10 volt and 10 farad and 20 farad. So the resultant is going to be a 30 farad capacitor. So I guess it's something to celebrate. So what if you want to have something of a 6.65 farad capacitor? So let's say you want to, for some weird reason, 6.67 farad capacitor. How are you going to achieve that? We still need the 10 farad and the 20 farad capacitors. So let's set them up. But here we're going to use a different structure. Well, I guess you can pretty much guess from now on that it's going to be in series. So what happens when we connect them in series with one another? And we have going to have a power supply right here. So this is going to be the 20 farad one. This is going to be the 10 farad one. So once again, this is going to be a 10 volt power supply. It's going to be a 10 volt power supply, and it's going to release 300 coulombs across the entire circuit. So what happens really? All these 300 coulombs, they enter into this plate, stored as negative charge in this negative plate. So 300 coulombs get stored on this plate. So 300 coulombs of charges are going to get out from this plate. And all those 300 are going to get into this plate and at the same time go out of this plate. And so at the end, in the entire circuit, the charges or the total number of charges remain constant, which is 300 coulombs across all of these capacitors. So what if we want one capacitor that has the same property as two of them in series? So we know that in series, the voltage divides, but the current remains constant, which means the charges remains constant. Sorry, once again. But the charges remain constant. So let's set up some other equations as well. So right here we could really use V total, which is basically the voltage across the power supply. It's going to be equal to the voltage across capacitor 1 plus voltage across capacitor 2. Okay, so instead of voltage, let's use this formula, and instead of voltage we can write it as Q by C. Okay, so the voltage so the total voltage across the entire circuit is going to be equal to the total current across the entire circuit divided by the total capacitance. So I would write it as C total, and that's equal to the charge across capacitor 1 plus the charge stored on capacitor 2. The charge stored in capacitor 2. Okay, now we know that the charge stored on capacitor 1 is equal to the charge stored in capacitor 1 is equal to the charge stored on one plate of capacitor 2, and that's equal to the total number of charges that gets out of the power supply. So by that we could really factor them out, and we get 1 by C total, or the total capacitance, is equals to 1 by C1 plus 1 by C2. And this is how you can figure out the total capacitance if you're using the capacitors in series. So let's really do the math. So we had a 10 farad capacitor plus a 20 farad capacitor. That's going to give us 3 by 20. But this 3 by 20 is 1 by C total, or reciprocal of the capacitance. So if we take the reciprocal of this, C total is going to be 20 by 3, which is 6.67. Yep, 6.67. So we have a 6.67 farad capacitor right now, as we wanted. So I guess you've had enough cringe for today, and this is pretty much everything that you need for doing the A-level capacitance topic. So I really hope that you enjoyed the video, and don't forget to check out the other videos on this channel.